Welcome to Dunwoody College of Technology, Mechanical Engineering, Statics, Quiz 5 from fall 2019, excuse me. So in this problem, we have an applied force acting at point B on the C channel. We're given what that force is. Excuse me. So we're given what that force is. We're acting there, and we're asked to find the moment of this force about point A. So point A is back here on the z-axis. It's on the same plane, plane parallel to the xy plane as point B, and we need to find what that moment is. And I ask, does that result match our intuition, and then what's the magnitude of that moment? I give you some points here. You get points for a position vector, RAB. You get points for the setup of the moment, calculation for the correct moment, 1 point for the intuition, and then 2 points for the magnitude. So looking at this, we need to find RAB, which is the position vector from A to B, and that's just the difference between their positions. So step one, we're going to find a position vector, RAB. Step 2, use the cross product to find moment, and then we'll answer the intuition and then find the magnitude of our moment. So step 1, position vector, RAB. We're ending up at B, starting from A. Oh, my arrow went away. There's RAB again. So in the x direction, we're going all this way. So we're going 8 feet in the x direction. In the y direction, we're moving from the xz plane over this way. So we're going this far in the y direction. And in the z, we're in the same position in z. So our position vector is 8i plus 0.25 j plus 0 k hat, and that would give us units of feet. So there's our position vector. Step 2, our cross product. So our moment about point A is going to be RAB cross F. And what is that? In determinant form, we have I hat, J hat, K hat. Then we have our position vector, so what we just found, 8, 0.25, 0. And then we have our force up at the top there, is 250, 50, and negative 450. Alright, so then we'll go through and do our cross product. So we'll cover up the I column, and we do 0.25 times this minus that, right? So we have 0.25 times negative 450 minus 0. That's all of our i's. And so our 0 times 50 made that 0. Then we have negative, doing it the book way here, so we're covering up the j column, so we have negative 850 times negative 800 times negative, 8 times negative 450 minus, what do we have the other way, 0 times 250, 0, it's a j hat, and then plus, covering up the k column now, 8 times 50 minus 0.25 times 250, that's k hat, ran off the edge there. So when I put this together, I get negative 112.5 I plus, so my negative goes positive, plus 3600 j hat plus 337.5 k hat. My units there will be pound-feet. So that's my moment. And I may want to simplify that down to 3 significant figures. I'll go with 4 for the time being. Now, does that make sense to us? Looking at our applied force, our largest moment arm from A is in the x direction, right? So going over this way in the x direction, here we are, and that is going to be multiplied by our biggest component of the force, which is in the negative z direction. So there's the Fz times our x offset of 8 feet, and that's our biggest part. That makes sense to me. It gives us a positive moment, right? If I was pushing down here, I'd expect that to rotate this way around y, or counterclockwise. It gives me a positive moment. So that does match my intuition. Since our moment arm is in x, force is mostly in z, so our moment in y. Alright, so then lastly, our magnitude. So there's that. Yes, it matches it. Magnitude, ma, without the vector symbol, is going to be the square root of each of these terms here squared. So I get negative 112.5 squared plus 3600 squared plus 337.5 squared. And when I do that, take the square root, I get ma is 3601.8 pound-feet, or basically all of that j hat part is what comes through. So one key point here is we want to make sure that we cross R with F in that order. If we flip those around, we're going to get negative signs on this. It should be the same magnitude, it's just going to be flipped around. And so we need to remember to create the position vector, then cross it with the force vector. In this case, we are given the coordinates for the 2 points. Pretty easy to make the position vector from that. And then we are given the force in Cartesian vector notation.